Hi, I'm Amos Robinson. This is work done with two of my supervisors, Gabrielle Keller and Ben Lippmeyer. So, I'm going to talk about fusing filters with integer linear programming. And depending on how much you know about integer linear programming, it either sounds really scary or ridiculous overkill. But hopefully I can convince you that it actually isn't scary or overkill. So we've got some Fortran code here. Two loops. First loop, we're creating two sums, the sum of all the elements, the sum of the positive elements. Then you're creating two output arrays, dividing by each sum. So normalize, some sort of normalize function. But obviously we want to write it in Haskell. And yeah. But it's shorter. At least it's shorter. I mean, sorry?
Is it?
This is 5 lines. The other one was
very
10.
much stretched out.
See, I just was able to make the text bigger. So we've got five combinators, and we're getting the sum. Then we're normalizing the array based on the first sum, and we're finding only the positive elements, and then we're summing. And so you hope you can see that this is the same program, or much the same. Obviously, we want this to result in the same loops that our Fortran program. So we need fusion. And there are basically two kinds of fusion: vertical fusion and horizontal fusion. Vertical fusion, where we've got a producer and some consumer. So we fuse the producer into the consumer. Here, we've got y is the output of a filter, and then we're summing over this filtered output. So we want to produce, if we had a single combinator filter fold, which did these in a single loop, let's just imagine that we have this magical way of combining combinators into a single loop. Our prior work on data flow fusion with series expressions actually does something very similar to that. So we can assume that. Now, horizontal fusion, we've got multiple combinators working over the same input data. These both work on the x's input array. So if we had a map filter fold combinator, we could make them into one. So that's pretty cool. But now we're finished. We can't actually produce any more fusion from here, because we've got the output of fold here. Sum 1 is the output of a fold. The thing about folds is you only know the result once you've read all of the input. It's not like an online computation like a map is. And this map filter fold here relies on the sum 1. So we can't fuse them together. And similarly, we can't fuse these together because sum 2 is, again, the output of a fold. So what went wrong? We wanted our beautiful Fortran program with only 2 loops, but we ended up with this.
3 loops.
We wanted 2 loops.
Yeah, 1, 2.
Yeah,
only
sorry.
5, we have 3, we want 2.
Yeah. So what happened? We got this 3-loop abomination. So what went wrong? We had a few choices. At some point, we had a few choices of where we could apply the fusion, but we chose the wrong one. We really can't try all of the fusion, not today, at least. So let's try one more, just to see if we can get it right. I'm pretty happy with this horizontal fusion, so we'll keep it, the filter fold as before. But instead of null 1 and sum 2, instead of horizontally fusing them, let's fuse sum 1 and sum 2. They're both working over x's input, so we have a fold filter fold, which is a fold over the original data and a fold over the filtered data. Cool. now we've got these two maps, and they're both working over x's. Yeah, we can fuse those. Bam. Two loops. Cool. So, why was that order better than the other order? And how do we find which order is the best order without trying all of them? Well, it turns out this is an NP-hard problem. And what do we do when we've got an NP-hard problem? We give it to someone else. We say there are integer linear programming solvers, people who spend all their lives writing these amazing solvers, and I'll let them do that, and I'll do this. So what we want to do is convert our combinator program to an integer linear program that will tell us which order to apply fusion in. So here we've got an example integer linear program. It's fairly small. So we've got a set of variables, x and y, and they're both integers. Then we've got a set of constraints. So x and y must both be between 0 and 2. And x plus 2y must be greater than or equal to 3. And we want to find assignments to x and y that satisfy those constraints while being the minimal value for this objective function. So we want to find a minimal assignment to x and y that satisfies these constraints for this y minus x. And if you think about it, that's sort of like minimizing y while maximizing x. So we want the minimal value for y, 0, maximum value for x, 2. X is 0, x is 2 and y is 0. That doesn't actually fit this constraint. So we need to bump y up by 1. And we end up with the solution, x is 2 and y is 1. It gets a lot, these external solvers can deal with a lot more complicated than that, but hopefully that's got the idea across. So what we want to do is take our combinator program, create a ILP program, which we pass off to the external solver, and will tell us what to fuse. The first step is to create a graph from our combinator program. So we start with a node on the right for our input array x's, and then for each combinator, sum 1, we add a new node for that combinator. And it's a fold over the input array x's. So we add a edge from x's to sum 1. And then we keep going through all of the combinators. So nor1 is a map over x's, so there's an arrow from x's to nor 1. But there's this funny arrow here, and that's because sum 1 is a fold. So remember that folds can't really be fused with anything, or at least folds can't be fused with anything on the output edge. So this is a fusion preventing edge. No fusion is possible between these two. And we sort of continue doing this, adding nodes for each combinator, and we end up with a pretty plausible looking graph. We've got another fusion preventing edge here. But not all loops have the same size. We can't necessarily, or at the very least it gets tricky if we try to fuse a loop with 9 iterations with a loop with 47 iterations. It's just not easy. So we say, well, let's just outlaw it. You can only fuse loops together if we know statically that they have the same size. And what we do first is figure out what size each combinator's loop is. So sum 1 is a fold over x's, so it's going to loop over all of x's. Nor 1 is a map over x's, so it's going to loop over all of x's. So the loops for these are all size of x's. Y's is interesting though, because it's a filter. So it's going to read through all of the x's input array, but its output is going to be potentially smaller than its input. So its output size is actually y's. So sum2 only has to loop over size of y's. But that means that if we look at sum1 and sum2, they don't have the same iteration size. So we can't necessarily fuse them together.
We just say like it's a filter anyway, so we throw out like it doesn't matter if you do some extra computation. In this case.
Maybe.
And then
Maybe we could, like, yeah.
right,
no.
sorry. Sorry to derail.
Yeah. But, so what we say is that, well, we can fuse y's and sum2 together because that's like producer-consumer fusion. And we can't fuse sum1 and y's together because they're the same size. And if we fuse these two together, then the size of sum2 ends up becoming the size of its parent, which is x's, and we can fuse them together. So these two, despite having different sizes, we say that they can actually be fused, but only if sum1 and y's are fused together and y's and sum2 are fused together. So we need to express that in a linear integer program somehow. So what we do is add a new variable for each pair of nodes, say f of sum1 and sum2, and that's going to be either 0 if they're fused together, or 1 if they're not fused together. That sounds backwards, but it turns out that's necessary for some ordering constraints you'll see later. So what we say is that f of sum2 and y's must be less than or equal to f of sum1 and sum2. So if sum2 and y's are not fused together, then f of sum2 and y's will be 1. And 1 must be less than or equal to this 0 or 1, which forces this to be 1, disallowing them to be fused together. Now we need to decide what it means to be the best possible fusion clustering. So we go back to our graph and we look at each pair of nodes and we assign them a weight that we get from fusing them. These two, they look pretty good. They're both looping over the x's input array. So we're going to get a pretty big memory bandwidth improvement from fusing them together. So we say it's 100. These two, sum1 and sum2, not so much. They don't really operate over the same array, and there's no data flowing from them. So we say it's only 1. And the reason we have these numbers, 1 and 100, is that any number of these ones will never add up to or beat a 100. So we say if we've got a choice between 50 loop overheads or a single fusion that reduces memory traffic, we'll always choose the fusion clustering that reduces memory traffic. If we look at sum1 and nor1, well, they have a fusion preventing edge between them, so there's not much point even calculating the benefit of fusing them because they'll never be fused. And we continue doing this for each pair of nodes. Sum1 and nor2, they both loop over x's array, so there would be a benefit of fusing them. And we keep doing that until we've got all of the pairs of nodes. All of the pairs of nodes with no edges, fusion preventing edges between them. So now we've got these weights. We want to multiply each one by the f of the two nodes. So we want to minimize f of sum 1 and y's times 100. So you can sort of think of this as squeezing all the f's down to 0, as many f's as possible. And given the choice between squeezing this one or squeezing this one, it's going to choose this one because it gives more of a benefit. It's got more juice in it. But not all clusterings that we could implement as single loops can actually be joined together. So if you look at this, we've got the blue cluster, which is sum 1 and nor 2, and you could write a single loop that does that computation. With the red cluster, nor 1, y's, and sum 2, you could write a single loop to do that as well. But the red cluster relies on the blue cluster. So you can't perform the red cluster first. Similarly, the blue cluster relies on the red cluster. So you can't perform the blue cluster first either. So we can't actually execute either of these. So what we need to do is restrict it to only allow acyclic clusterings. And how we do that is by adding a new variable to each node, which is the index in the topological order of the node, of the cluster that node is in. So if you've got a non-fusible edge, then you just say that, well, sum 1 must be before nor 1 in the topological ordering, because they're not going to be fused together. And we just express that as the order of sum 1 is less than the order of nor 1. But it gets more interesting when you have a fusible edge. So if they're fused together, you want to say that their index in the topological order has to be the same. But if they're not fused together, well, sum 2 has to be strictly after y's in the topological order. So what we want to write is something like this, but that's not a linear constraint, linear function. So if f of some y's and sum 2 is 0, then they're the same, else less than. So we end up with this, which is 1 of f is less than or equal to the difference is less than or equal to 100. And in the case that they're fused, the f is 0, so the difference is from 0 to 0, and they must be equal. But if they're not fused, f is 1, and the difference is anywhere from 1 to 100. There are only 5 nodes in this graph, so 1 to 100, that's a big enough range for the number of indices in the topological order. In the final case, we have no edge between two nodes, and we want to say if they're fused together, they have the same index. If they're not fused together, we don't really care what they are. Maybe they're the same, maybe they're not. It doesn't actually matter. So we just say, if f is 0, they're the same. And that ends up being negative 100f is less than the difference, is less than 100. And if they're fused, again, the difference must be 0. But if they're not fused, the difference can be anywhere from negative 100 to a positive 100. So that leaves them essentially free enough to do whatever they want. And if we put this all together, we actually have an integer linear program that we can hand off to coin CVC or Cplex, and we can run it, and it'll tell us, sum 1 and y's should be fused together. Y's and sum 2 should be fused together. And sum 1 and sum 2 should be fused together. So that's a nice blue cluster. And nor1 and nor2 should also be fused together. And all the other things, they shouldn't be fused together. So that's the clustering that we wanted in our original Fortran program. Hopefully integer linear programming doesn't seem so scary after this, but we have an implementation of this that in our discipline disciple compiler, it uses small programs in adequate time, but we really need to look into bigger programs, and we only support a few combinations. Yeah.
Yeah. So you showed us a few combinations like format and filters. So I wonder if you have a way of characterizing what kind of combinators you support in your model and what kind of functions?
Not yet. At the moment, we only support map, filter, fold, map to, gather and cross product, and generate. So all fairly simple combinators to start with for now.
Does that give you zip also? For doing dot product kind of thing?
Yeah, so we could just say map to over comma.
Map to is zip with, but it requires the both input vectors to be the same one.
John?
So, two questions, or a question and comment. So what software are you using?
I was using GLPK, but I just wrote some bindings to Coin CVC, which is still open source, but tremendously faster than GLPK. I tried Cplex, and it's amazing.
Yes, yes.
So-
I was about to say, so there was work done at Bell Labs about 15 years ago on register allocation using ILT by Walt George and Andrew Appel, and I mean, looking at your encodings, they look actually very similar. They were able to scale up to like compiling the entire SML New Jersey compiler, doing register allocation for the x86 on that in reasonable amounts of time using Cplex. And a lot of that came down to sort of really engineering the encoding of the problems and to make sure that the ILP works. You might want to actually go back and take a look at that paper. It was probably a PLBI or maybe a POPL paper.
Okay.
It's probably around 2000. Earlier than that.
Cool.
Right. Okay. So you're using integer linear programming, which is also, which of course is NP hard and so on. Whereas just linear programming with reals is usually nice. So I was wondering, would it be possible instead to do something where you solve it for reals or rationals or whatever, and then you have you might be able to say, oh, these probably need to be fused together, these probably need to be fused together, and then implement some sort of strategy.
I'm not.
I don't know whether there's anything to be gained from
You
that.
can talk about doing rounding on linear programs also. That's another way around. Although you don't. That's a whole sentence. It's an entire book.
It's called Lagrange relaxation.
Okay.
I have a hunch that if we were to relax it to reals, we'd end up with 0, 0, 0, 0.00001, and so on.
Ah, okay.
Like everything just an epsilon above 0.
Okay.
But I don't know.
Let's take two last questions. Done.
Okay. So you have to know what the possible choices are, right? So you have to start your program when you start to do this analysis of which one's the best choice, you need to know all the combinators that you've got at the right phase during compilation, right?
Yes, we need all the.
Which can be a tricky thing because you might not know them until you've done a few unfolderings. Or do you have a strategy for ensuring that you find out all of them at the right time simultaneously, rather than you could end up in sort of phasing problems? Or I find out the first three, but I didn't discover the other two until later, and I didn't know all the possible combinations. Do you see what I mean?
Yeah, so we don't really have a story for that right now. At the moment, I've been just thinking do all the inlining we can, and then do all the inlining except for combinator definitions.
Inline everything, but don't inline the ones that you want to match on.
Yeah.
Wait when you've done enough inlining, then do this analysis, and then go back to inlining again afterwards.
So that's the rough idea at the moment.
Can we take the last questions offline because we're running out of time? So let's take the speaker again.